10 days ago, 4 human beings climbed into a metal capsule the size of a large fan and traveled farther from Earth than any person in recorded history. They came home alive, and that fact, that single remarkable fact, is being celebrated everywhere right now. The headlines are calling it triumphant. The press conferences use words like historic, groundbreaking, a giant leap. Social media is full of people watching the recovery footage with tears in their eyes. And honestly, if you watch those 4 astronauts walk across that flight deck on the USS John P. Murtha after 10 days in deep space, if you saw Victor Glover saluting the crowd and Christina Koch looking up at the people gathered on the decks above her with that expression of someone who has just returned from somewhere genuinely unreachable by ordinary imagination, you felt something real. You felt it because it was real. But there is something those press conferences are not telling you. Something buried inside the data that came back with the crew. Something that the mission itself revealed, not about how ready we are to go deeper into space, but about how close we came, on multiple occasions during those 10 days, to a very different kind of ending. Something that changes the entire meaning of what we just watched, not by diminishing it, but by placing it inside a context that the celebration coverage has been remarkably careful to avoid. And by the time we finish this conversation, you're going to understand exactly what Artemis II actually proved. Not what NASA wanted it to prove. Not what the headlines say it proved. Not what the inspirational social media clips suggest it proved. What the physics, the biology, the engineering data, and the mission's own internal records say it proved. Because those are not the same story. Not even close. Stay with me, because this is more interesting, more consequential, and more genuinely important than anything the press release version of Artemis II contains. Let us start with something that almost nobody in mainstream coverage is talking about. For 7 consecutive days during the Artemis II mission, radiation alarms inside the Orion spacecraft never stopped sounding. 7 straight days. Not a spike. Not a brief alert that resolved after a few hours. A sustained, continuous, unrelenting bombardment of charged particles that no shield on that vehicle could fully block, that no mission planner had confidently predicted at that intensity prior to launch, and that the crew could do almost nothing about except monitor the readings, document the data, follow their protocols, and wait for the environment to change. Now, before you ask whether the crew was actually in danger, the answer is genuinely nuanced, in a way that should make you think much more carefully than the celebration coverage has encouraged you to think. The short answer is that they received a manageable dose for a 10-day mission. The accumulated numbers fell within acceptable ranges. They are home. They are healthy. They walked off that ship on their own 2 feet with remarkable steadiness for people who had just spent a week and a half in weightlessness. And every single person watching those recovery videos experienced something genuinely moving. But the long answer, the answer that matters for everything that comes next, is that manageable for 10 days and manageable for the mission after this one are not the same statement, not even remotely the same. And understanding exactly why requires understanding something fundamental, something that most space coverage glosses over so quickly it barely registers. You live inside a force field. You have lived inside it every single day of your entire life. You have never once felt it, seen it, needed to think about it, or had any occasion to be grateful for it in a conscious, specific way. It is called the magnetosphere, and it is generated by the convection of molten iron deep inside Earth's outer core. That movement of electrically conductive material through its own magnetic field creates a planetary magnetic field that extends tens of thousands of kilometers out into space in every direction, forming an invisible shield around our entire world. That field does something extraordinary. It deflects the vast majority of charged particles streaming constantly through our solar system, particles originating from the sun, from distant supernovas, from extreme astrophysical events that occurred billions of years ago across the galaxy. Protons, electrons, heavy ions carrying enormous kinetic energies. Most of the cosmic radiation environment that would otherwise strike our surface directly gets bent harmlessly around us. The particles are channeled toward the poles where they interact with the upper atmosphere and produce the aurora borealis and the aurora australis, one of the most beautiful natural phenomena on Earth, which is in a very real sense the visible evidence of our planet's protective shield doing its job. Without the magnetosphere, those particles would strip our atmosphere away over geological timescales and irradiate every living organism on the surface into non-existence. Life as we know it on this planet exists because of that invisible field. Every organism that has ever lived here, every ecosystem, every civilization, everything has been protected by it continuously and completely, so thoroughly that we evolved with no biological mechanism whatsoever to detect radiation at dangerous levels because we had never needed one. The moment a spacecraft crosses beyond that bubble, the protection vanishes entirely. The International Space Station orbits at roughly 400 kilometers altitude. It sits well inside the magnetosphere. The crew there receives radiation exposure significantly elevated compared to people on the ground, and ISS astronauts do accumulate health risks from that exposure over long missions, but they are still within the shield. They are still inside the bubble. The magnetosphere is still doing most of the work of protecting them from the full cosmic radiation environment. Artemis II was not inside that bubble for most of its mission. Once Orion crossed the magnetopoles, the outer boundary of Earth's magnetic influence, those 4 astronauts entered an environment that is, from a radiation physics perspective, categorically, fundamentally, qualitatively different from anything experienced in low Earth orbit. Different, not in degree, but in kind. The comparison between ISS radiation exposure and deep space radiation exposure is not the comparison between standing outside on a sunny day versus standing outside on a cloudier day. It is the comparison between standing outside versus having no atmosphere or magnetic field at all, with the full output of a star and the cosmic radiation of the galaxy hitting you directly. In deep space beyond Earth's magnetosphere, a crew is exposed to 2 primary radiation sources simultaneously and continuously. The first is solar energetic particles, bursts of protons and heavy ions accelerated by solar flares and coronal mass ejections. These events are sporadic, sometimes extraordinarily violent and impossible to predict with any useful precision more than a few hours in advance. You get a warning sometimes that something has erupted on the sun's surface. By the time the particle stream arrives, you have had perhaps an hour to prepare, perhaps less, depending on the event's characteristics. The second source is galactic cosmic rays, high-energy particles originating from outside our solar system entirely, accelerated by supernova remnants, neutron star collisions, and other extreme astrophysical events scattered across the galaxy over billions of years. These are not the sun's particles. They come from everywhere at once, from every direction simultaneously, from events so distant and ancient that the light from the original explosions has long since dissipated into the expanding universe. Galactic cosmic rays are constant. They do not surge and recede with the solar cycle like solar energetic particles. They are always present in deep space, always penetrating, always interacting with whatever matter they encounter, and they carry energies that make them almost impossible to shield against with any practical quantity of material on a spacecraft that still has to actually launch from Earth. During the Artemis II mission, according to the 6 radiation dosimeters distributed throughout the Orion capsule, the crew's total radiation exposure over approximately 9 days beyond the magnetosphere was roughly equivalent to what a person standing on Earth's surface would receive over an entire calendar year. Let that settle for a moment. 1 day in deep space, 1 year of normal background radiation. That ratio is not an estimate from a theoretical model. It is the actual measured output from the actual sensors on the actual spacecraft that actually carried 4 actual human beings around the actual moon and brought them home. Those numbers are real, and they're manageable for 10 days. The crew accumulated somewhere between 12 and 15 millisieverts total during the mission. NASA's career exposure limit for astronauts is 600 millisieverts. On paper, for a 10-day mission, this works. The numbers fit. Everything is within acceptable parameters and the crew is home healthy. But here is the calculation that nobody wants to put in the headline. The number that changes everything. The number that reveals exactly why the manageable story for Artemis II is also, simultaneously, the not manageable story for what the program is supposed to lead toward. A Mars mission lasts 900 days. Not 10, 900. When you multiply the daily deep space radiation exposure rate documented during Artemis II across the duration of a Mars round trip, including transit phases beyond Earth's magnetosphere and surface operations on a planet with no global magnetic field of its own, the total accumulated dose comes to approximately 1,000 millisieverts. NASA's career limit is 600. A single trip to Mars and back would expose every crew member to nearly 70% more radiation than NASA considers acceptable across an entire career. And that career limit is not a conservative, ultra-cautious, excessive safety margin number. It corresponds to roughly a 3% increase in lifetime cancer mortality risk, a level that NASA and its medical advisors have determined represents reasonable, acceptable risk for a career in spaceflight. At 1,000 millisieverts, the estimated excess cancer risk rises to somewhere between 5 and 10%, depending on the model used, the individual crew member's age, their sex, and their personal genetic radiation sensitivity. Some models using different assumptions about the biological effectiveness of heavy ion radiation put the upper uncertainty bound as high as 20%, 1 in 5, a 1 in 5 chance that the act of making the journey itself, not an accident, not an equipment failure, not a miscalculation, just the physics of existing in deep space for 900 days, gives a crew member cancer that eventually kills them. The European Space Agency, not a fringe scientific voice, but one of the most respected and rigorously conservative institutions in the history of human spaceflight, has published assessments stating directly that a crewed Mars mission is not currently viable due to radiation exposure alone, not challenging, not requiring further engineering development, not achievable with incremental improvements to current shielding technology, not viable. And when you hear that, your first instinct, the instinct that every person has when confronted with a shielding problem, is obvious and completely reasonable. You think, just add more material, thicker walls, more water tanks, denser composites. Surround the crew sleeping area with as much mass as possible and block the radiation. The problem is that galactic cosmic rays are not ordinary radiation, in the sense that most people imagine when they think about shielding. A galactic cosmic ray, heavy ion, an iron nucleus, for example, can carry billions of electron volts of kinetic energy. When it strikes a shielding material, whether aluminium, polyethylene, water, or anything else we have ever manufactured, it does not simply stop and deposit its energy in the material. Instead, it fragments. The primary particle breaks apart, and its daughter particles, along with displaced nuclei from the shielding material itself, produce a shower of secondary radiation, neutrons, lighter ions, fragments of various types that spray through the interior of the spacecraft in all directions, in some shield configurations and some particle energy ranges. The secondary radiation dose inside the vehicle is actually higher than the primary radiation dose would have been without any shielding at all. This is called secondary particle generation, and it means that beyond a certain optimal thickness, adding more shielding material does not reduce crew exposure, it increases it. There is an optimal shielding thickness for any given material, a point of maximum net dose reduction, and even at that optimal point for galactic cosmic rays, the achievable dose reduction is approximately 20 to 30% regardless of how much additional material you add beyond the optimum. You cannot engineer your way to zero. You cannot engineer your way anywhere close to zero. The physics of how high-energy particles interact with matter simply does not cooperate with the intuitive solution. So what did the Artemis II crew actually do during the most intense radiation period of their mission? What does the state of the art look like in practical terms in the year 2026 for protecting human beings from deep space radiation? On Flight Day 8, when the continuous elevated particle flux readings had been going on for nearly a week, and the combination of solar energetic particle events and high-speed solar wind streams from coronal holes had kept the radiation environment persistently elevated, the crew performed a procedure called HERA, Human Exploration Radiation Assessment. They built a shelter out of whatever dense materials were available inside the capsule. Equipment bags, water containers, supply packs, anything with enough mass to attenuate the particle flux even slightly was repositioned to create an improvised shielding barrier around the sleeping area. Water is particularly useful for this because hydrogen, the lightest element, is one of the most effective radiation absorbers per unit mass, and water contains a high density of hydrogen atoms per volume. Stacking water containers between the crew and the radiation source reduces the dose rate inside that area. It worked, modestly. The measured dose rate inside the shelter was detectably lower than outside it, but the shelter was designed for temporary use during a severe solar particle event. 24 hours of marginal additional protection, roughly. It cannot be maintained continuously for days or weeks without completely disrupting mission operations. The crew has work to do, systems to monitor, procedures to execute, and you cannot run a spaceflight mission while permanently crammed into a sleeping area surrounded by cargo bags. And the shelter provided virtually no protection against galactic cosmic rays, which carry energies high enough to penetrate meters of any material we have ever manufactured, not improvised cargo bag walls. This is the state of the art, the most sophisticated human spaceflight program in the world. In the year 2026, protecting its crew from deep space radiation by building a fort out of luggage. And I say that not to mock anyone involved in the mission, not to minimize the genuine brilliance and dedication of the thousands of people who worked on Artemis II, but to be honest about what that image represents, about where we actually stand, relative to where the narrative says we are headed, because the shelter on Artemis II was not a solution. It was an acknowledgement. It was the engineering equivalent of NASA saying out loud, in the language of mission procedures and mission protocols, we know we cannot fully protect you from this environment. Here is the best we can currently offer. A wall of water bottles and gear bags between you and the cosmos. And the reason that acknowledgement matters beyond the immediate mission is that Artemis II lasted 9 days and required the shelter for one radiation event during one short trip. Multiply that by the duration of a Mars mission. Not one event, every event, plus the continuous baseline of galactic cosmic rays that never sleeps, never pauses, and carries enough energy through any practical shield to remain a significant health threat throughout the entire journey. There is no version of the cargo bag fort that solves a 900-day exposure problem. There is no incremental improvement to AV-SOIT, and there is no upgraded water container arrangement that closes the gap between what we demonstrated on Artemis II and what Mars actually demands from a radiation protection standpoint. Now I want to tell you something that makes the radiation story even more visceral, because it involves a moment in real history that reveals exactly how much of what we call success in deep space exploration has depended on timing rather than technology, on fortune rather than engineering. In August of 1972, between the Apollo 16 and Apollo 17 missions, the Sun produced one of the most powerful solar particle events ever recorded in the instrumental era of space weather observation. Scientists refer to it as the August 4th event, and it was extraordinary by any measure. The event released a torrent of high-energy protons so intense that had an astronaut been in deep space, unshielded by Earth's magnetosphere during the event, the estimated radiation dose would have been approximately 26 sieverts, not millisieverts, not microsieverts, sieverts. A dose of 5 sieverts is the threshold considered universally lethal within weeks, causing radiation sickness so severe that the body's ability to repair itself collapses entirely. At 26 sieverts, death would not come in weeks. It would come in hours. The bone marrow would be destroyed. The gastrointestinal lining would hemorrhage. The central nervous system would fail. There is no medical intervention, no amount of supportive care, no pharmaceutical treatment that exists which would have meaningfully altered the outcome. 26 sieverts in deep space is a death sentence measured in hours. Apollo 16 returned to Earth in April of 1972. Apollo 17 launched in December of 1972. The August storm fell almost exactly in the middle of that 8-month gap. If Apollo 16 had launched several months later than it did, the crew would have been beyond Earth's magnetosphere when the event hit. If Apollo 17 had launched several months earlier, same outcome. The gap between those two missions happened to be positioned precisely during one of the most lethal solar events of the entire 20th century. They were not protected by engineering. They were not protected by foresight or prediction. No mission planner predicted the August 4th event far enough in advance to do anything about it. They were protected by the fact that no human being happened to be in deep space when it occurred. They were protected by the accident of the schedule. Now apply that same physics, that same solar unpredictability to Artemis II, the same star. The same fundamental inability to predict extreme events more than hours in advance. The same absence of any shielding solution that would have protected a crew from a 1972 class event. Orion's improvised shelter and its passive shielding offer meaningful protection against moderate solar particle events, the kind that produce doses in the range of tens to low hundreds of millisieverts. They offer no meaningful protection against a 1972 class event. The The shelter would have reduced the dose, yes, but the math does not close. Not remotely. An event of that magnitude hitting the Artemis II crew in deep space would have been a fatal emergency with no adequate response available. And the Artemis II crew was in deep space for 9 days. During those 9 days, the sun threw moderate punches, a G2 geomagnetic storm, an M-class solar flare, 7 days of elevated electron flux, but nothing at the extreme end of the scale. Nothing in the ballpark of what August of 1972 produced. The reason the crew came home healthy is partly extraordinary engineering and extraordinary mission planning and extraordinary human courage. And partly, it is luck. Not entirely luck, not predominantly luck, but partly. And partly is not a word that belongs in the engineering validation of a program whose next steps involve 900 days in that same environment. Mission survival in deep space remains partially probabilistic, not fully controlled. That sentence should be printed on the wall of every conference room where future mission planning takes place, because probability does not improve with familiarity. The sun does not become safer because we have flown through it before. The statistics of extreme solar events do not bend toward human convenience because we really need them to. The probability of encountering at least one severe solar particle event during a 3-year Mars mission, depending on where the mission falls within the sun's 11-year activity cycle, is somewhere between 15 and 25%. You roll a 4-sided die. If it comes up 1, the crew receives a dose that may be lethal and is certainly career-ending on a mission from which there is no early return, no rescue, and no way to get anyone home faster than the orbital mechanics of 2 planets allow. That is not a fringe risk assessment from a pessimistic analyst. That is the statistical reality of the deep space radiation environment applied to the mission duration required for Mars, and it represents one of the hardest physical constraints facing the entire program. But the radiation story, as genuinely alarming as it is when you look at the full numbers, was not the only part of Artemis II pushing against the limits of what we have actually built and validated. Because while the engineers were watching radiation monitors, they were simultaneously, quietly, anxiously watching something else. Something that had been the subject of intense internal discussion inside NASA for nearly 3 years before this crew ever left the launch pad at Kennedy Space Center. The heat shield. Let me take you back to December of 2022, because that is where this particular thread begins. NASA's uncrewed Artemis I mission completed a 25-day test flight around the Moon, the first flight of the Orion capsule with the Space Launch System, and the mission was declared a success by every public measure. 4 astronauts were not on board, no crew was at risk, and the vehicle performed its primary functions adequately enough to justify moving forward. But when engineers recovered the Orion capsule from the Pacific Ocean and brought the heat shield back to the laboratories at Kennedy Space Center for detailed inspection, they found something they were not expecting and had not predicted: damage at more than 100 locations across the surface of the AV-Seota ablative heat shield. Instead of eroding in the smooth, controlled, predictable fashion that years of thermal modeling had projected, the material had cracked at boundaries between the pre-machined blocks that made up the shield's surface, and large chunks had broken away entirely during re-entry. A failure mode called spillation, where internal pressure builds up inside the ablative material and pieces literally pop off under thermal stress rather than charring and eroding smoothly as designed. Understanding why this happened required understanding how the AV coat system works at a fundamental level. AV coat is not a heat-resistant shell in the conventional sense. It is an ablative system, designed not to resist heat but to absorb it and carry it away from the vehicle through controlled self-destruction. The material absorbs enormous thermal energy, chars, and the charred layer erodes away, taking the heat with it into the airstream rather than allowing it to conduct through to the crew cabin. The shield sacrifices itself to save the crew. The critical requirement is that this sacrifice happen in a predictable, controlled, well-understood manner. Because if the erosion rate is too slow, heat penetrates the underlying structure, and if it is too fast, you run out of shield before you run out of atmosphere. The Artemis I investigation, which took 2 years and more than 120 individual ground tests to complete, eventually identified the root cause. The skip re-entry profile used during Artemis I, where the capsule dips into the upper atmosphere, bounces back out briefly on aerodynamic lift, then plunges back in for final descent, created a thermal cycling pattern that no model had fully accounted for. Heat, then a brief cooling phase when the capsule exited the atmosphere, then intense heat again. That cycling caused gases trapped inside the AVCO8 block structure to expand and contract repeatedly, generating internal pressure at the boundaries between blocks that eventually exceeded the material's cohesive strength and ejected chunks. By the time engineers fully understood the problem and confirmed the root cause with sufficient confidence, the Artemis II capsule was already built. The heat shield was already attached. The manufacturing timeline for a replacement would have introduced years of additional delay into a program that had already been delayed multiple times and was under significant political and budget pressure to demonstrate progress. NASA made two changes. They abandoned the skip re-entry entirely and switched to a steeper direct entry profile, one continuous plunge to the atmosphere without the bounce that created the damaging thermal cycling. And they reformulated the AVSO material itself, reducing its porosity from approximately 6 to effectively 0, creating a denser material that would trap less gas internally during heating. Both of those sound like the correct engineering response, and they may well be exactly the right fixes. The engineering reasoning behind both changes is sound. The physical logic is defensible, but here is the part that engineers who have reviewed the program from the outside have raised as a genuine concern, and I want to be precise about this because it is easy to mischaracterize. The redesigned heat shield, with the new zero porosity AVCO formulation and the new steeper direct entry profile, had never been tested together at lunar return velocity with a crewed vehicle. In standard aerospace engineering practice, the validation sequence goes like this. You identify the failure mode, you develop a proposed fix, you test the fix in the relevant environment as closely as you can approximate it on the ground. You validate that the fix actually addresses the failure mode without introducing new failure modes. You confirm your confidence in the fix is high enough to justify putting human beings on the vehicle. Then you fly. What the Artemis II timeline required was a compressed version of that sequence, where the ground testing, while extensive, could not fully replicate the actual re-entry environment at lunar return velocities with a crewed capsule, because the only way to do that is to actually fly the mission. The reformulated material behaves differently under thermal stress than the original formulation. The direct entry profile creates a different heating distribution across the shield surface than the skip profile did. Those two changes were implemented together, which means that individual contributions to shield performance cannot be cleanly isolated from each other. The first complete real-world test of the new configuration under actual lunar return conditions was Artemis II itself. It worked. Every available indicator suggests the heat shield performed within acceptable parameters. The crew is home. The capsule is being analyzed right now at Kennedy Space Center, and when those results come back, they will tell us a great deal about exactly how the new design performed under the actual conditions of the mission. That information is critically important for everything that follows. But it worked is not analytically equivalent to we fully understand why it worked, and we understand why it worked is not the same as we can confidently extrapolate to what comes next. Because what comes next in the trajectory that the entire program is building toward is a return from Mars. A spacecraft coming back from Mars will hit Earth's atmosphere at approximately 14 kilometers per second. Artemis II hit at approximately 11 kilometers per second. The numerical difference is 3 kilometers per second, roughly 27% faster. That sounds manageable. It sounds like a moderate engineering increment, the kind of thing you address through refinement and testing of existing approaches. But the physics of atmospheric entry does not work that way at hypersonic speeds. Above approximately 10 kilometers per second, the dominant mechanism of heating is not convective heating from friction, but radiative heating from the shock layer. The compressed plasma that forms in front of the vehicle as air is violently compressed beyond its ability to stay molecular, ionizing into a superheated plasma that glows with temperatures approaching those of stellar surfaces. Radiative heating scales approximately with the 8th power of velocity. The 8th power. A 27% increase in velocity produces not a 27% increase in radiative heating, not even a 200 or 300% increase, but approximately a 700% increase, 8 times the radiative heat load. The physical environment of a Mars return re-entry is not a more challenging version of the same problem Artemis II solved. It is a categorically different physical regime that no crewed vehicle has ever entered. that no heat shield of any configuration has ever been tested with human life depending on the outcome, and that the thermal models used for current systems have not been validated for. NASA's own internal technical roadmaps acknowledge this explicitly. The Mars return entry problem is categorized as a critical technology gap. That is the formal language for a capability that does not currently exist and must be invented before the mission can proceed. Now I want to turn to something that the Artemis II crew observed during their mission that has received almost no attention in mainstream coverage, despite being genuinely scientifically significant and directly relevant to everything we are discussing. While passing near the lunar surface during the flyby phase of their mission, the crew documented 6 meteoroid impacts on the Moon within a single hour. 6 visible flashes of light, objects striking the lunar surface at speeds of tens of kilometers per second, releasing enough kinetic energy on impact to be visible from orbit. This was the first time in the history of human spaceflight that meteoroid strikes had been directly witnessed in real time by human eyes in deep space. Ground-based telescopes and robotic orbital cameras have been recording lunar impacts for years, but having trained human observers at close range, able to document the events in real time with the context of direct human perception, added something genuinely valuable to the scientific record. But beyond its scientific value, that observation is a data point about the nature of the space environment that matters enormously for mission planning. The space between worlds is not the serene, empty, silent void that photographs make it appear. It is a shooting gallery, a constant stream of debris ranging from subatomic particles to objects large enough to leave craters kilometers across, moving at velocities that most people's intuition about physical impacts simply cannot accommodate. At 50 kilometers per second, a particle the size of a grain of rice carries the kinetic energy of a small hand grenade. A particle the size of a marble carries enough energy to punch through the outer hull of a spacecraft, and while the probability of a catastrophic impact during any given day of a mission is extremely low, the probability across 900 days of a Mars transit, surface stay, and return is something that mission planners cannot dismiss as negligible. The microparticle environment also matters below the catastrophic threshold. Continuous bombardment by dust-sized particles erodes surfaces, degrades thermal coatings, pits optical sensors, and slowly compromises the integrity of seals and joints that are keeping the crew alive. In the relatively well-characterized environment of low Earth orbit, where the ISS has had to perform debris avoidance maneuvers dozens of times, and where cupola windows have been replaced due to impact pitting, these effects are real and require ongoing management. In interplanetary space, where there is no tracking network, no collision warning system, and no option to maneuver out of the way of an undetected threat, they become a design constraint that adds mass complexity and maintenance burden to a vehicle that is already operating at the edge of what can be launched from Earth and kept functional for 3 years. The 6 impacts in 1 hour were a small observation from a brief encounter, but they were a reminder from the universe itself that the silence of space is an illusion, and the illusion becomes more dangerous the longer you commit to living inside it. Let us now talk about what space does to the human body when you stay long enough. Not the body of someone spending 6 months on the International Space Station, which is challenging enough, the body of someone spending 2.5 to 3 years on a round trip to Mars. Because the physiological picture at that duration is not a linear extension of what we know from ISS research. It is something we have genuinely never fully studied and may not be able to fully study without actually sending someone there. The human body evolved over millions of years under a very specific set of environmental conditions. 1 unit of gravitational acceleration, 1 atmosphere of pressure with a particular oxygen and nitrogen composition, a 24-hour light-dark cycle driven by Earth's rotation, and the continuous protection of the magnetosphere against cosmic radiation. Those are not arbitrary parameters. They are the conditions under which every biological system in the human body was optimized by evolutionary selection pressure across geological timescales. Remove any one of them and the body begins to malfunction in measurable, documented, sometimes irreversible ways. Remove all of them simultaneously, as a Mars mission would, and the malfunctions compound into a cascading physiological deterioration that no exercise regime, no pharmaceutical protocol, and no amount of human determination can fully prevent. Start with the skeleton. In microgravity, the mechanical loading signals that bone tissue requires to maintain its density disappear. Every step you take on Earth, every moment of standing, every shift in posture generates mechanical stress in the load-bearing bones of your body. And that stress is the signal your skeletal system uses to regulate bone formation. Without gravity, those signals vanish. The cells responsible for breaking down bone continue their work. The cells responsible for building new bone receive no signal telling them to keep pace. The net result is a loss of roughly 1 to 1.5% of bone mineral density per month, concentrated in the hips, spine, and legs. Exactly the bones you need to function when you arrive somewhere with gravity. Over a 6 to 9 month transit to Mars, before the crew has even arrived, they can lose 10 to 15% of their bone density. That is the equivalent of decades of age-related osteoporosis compressed into months. And studies of long-duration ISS crews where the mission is 6 months have consistently shown that even a year after returning to Earth, some crew members have not recovered their pre-flight bone mineral density. Not fully. The loss is not completely reversible within the study periods examined. The muscular system follows an almost identical trajectory, despite daily exercise protocols on the ISS requiring more than 2 hours of combined resistance and aerobic training. Losses of 20 to 30% of muscle mass have been documented in crews over 6-month missions. 2 hours every single day for 6 months, and you still lose roughly a quarter of your muscle mass, concentrated in the postural muscles and leg muscles that are most critical for functioning under gravity. The exercise slows the loss. It does not prevent it, and on a Mars mission where the transit phase is 9 months, followed by a surface stay in Martian gravity, which is only 38% of Earth's gravity, followed by another 9 months of weightlessness for the return, the cumulative muscular deterioration extends beyond any timeline we have studied or any countermeasure we have validated. The cardiovascular system adapts to microgravity in ways that create significant problems upon return to any gravitational environment. Without gravity's demands on the heart to pump blood vertically against a pressure gradient, the heart gradually reduces its output, the blood volume decreases, and the cardiovascular system becomes optimized for a condition that does not exist anywhere the crew needs to actually function. When they arrive at Mars after 9 months, they will have adapted cardiovascular systems that are deconditioned for the demands of even 38% gravity, let alone the demands of working in pressurized suits, carrying equipment, moving across terrain, and performing the physical tasks that the mission requires from the first day on the surface. There is no recovery period built into the schedule. The mission timeline is set by orbital mechanics, not by human physiology. You land, and then you work, regardless of what your cardiovascular system has been doing for the past 9 months. The vision issue is perhaps the most alarming discovery of the entire ISS research era, and it is alarming precisely because it is still poorly understood. Spaceflight-associated neuroocular syndrome, SANS, has been identified as a significant risk for long-duration spaceflight. In microgravity, fluid redistribution toward the head increases intracranial pressure, which presses on the optic nerves and physically reshapes the eyeball itself. The result is measurable changes in visual acuity that have been documented in real astronauts returning from real missions. Some crew members have returned from ISS missions with permanently reduced vision that did not fully recover after returning to Earth. The mechanism is not fully characterized, the long-term consequences are not fully understood, and there is no reliable, validated countermeasure currently in use. Visual acuity matters enormously for a Mars crew performing surface operations, maintaining equipment, reading instruments, and doing the careful, precise work that a mission with no resupply and no repair option from Earth demands. Add to all of this the immune suppression that occurs in microgravity, latent viruses that healthy immune systems ordinarily keep dormant, including herpes simplex, Epstein-Barr, and varicella zoster, reactivate in astronauts at measurably elevated rates compared to matched ground populations. White blood cell function changes in ways that reduce the immune system's effectiveness against novel pathogens. Wound healing slows measurably, and all of this is happening inside a closed, recirculated atmospheric environment where any pathogen that establishes itself has nowhere to go and 6 potential hosts, every one of whom has a compromised immune response in a habitat the size of a small apartment, now hold all of those physiological effects in your mind simultaneously. Bone loss, muscle atrophy, cardiovascular deconditioning, potential permanent vision changes, immune suppression, and remember that they're all occurring simultaneously on top of the radiation exposure we already discussed. which damages the same DNA that the body's cellular repair mechanisms are trying to fix. While those mechanisms are themselves impaired by microgravity, the effects are not additive. They interact. Radiation damages DNA. Microgravity impairs the cellular repair of DNA damage. The combination produces a biological environment inside the crew's own bodies that is more dangerous than either effect alone, and the synergistic interactions between them are among the least well-studied aspects of the entire long-duration spaceflight problem. Artemis II lasted 9 days, and the crew walked off the ship looking remarkably well. That is genuinely true, and genuinely impressive, and genuinely worth celebrating. But 9 days is not 900 days, and the physiological challenge at 900 days is not the same challenge multiplied by 100. It is a qualitatively different problem in a duration range that no human has ever actually experienced, and that no research program has yet fully characterized. And then there is the dimension that is hardest to quantify but in some ways most consequential of all: the mind. In the year 2010, 6 carefully selected volunteers entered a sealed facility at the Institute of Biomedical Problems in Moscow and did not emerge for 520 days. The Mars 500 study, conducted by the Russian Academy of Sciences in partnership with the European Space Agency, was the longest duration isolated confinement experiment ever completed. The participants lived and worked in a series of connected modules with a combined interior volume roughly equivalent to a modest house. They performed simulated mission tasks, conducted medical and psychological research, maintained systems, exercised according to prescribed protocols, and communicated with a simulated mission control using artificially introduced delays designed to replicate the communication environment of a real Mars mission. They were never actually in space. They were never in genuine danger. They could have walked out at any point, and the building they were confined in was located in an ordinary research campus in Moscow. Despite all of that, despite the absence of actual physical danger and the theoretical availability of an exit that they simply agreed not to use, the psychological effects across the 520 days were significant and documented in careful scientific detail. By the midpoint of the simulation, crew members were experiencing measurably disrupted sleep patterns, elevated fatigue scores on standardized psychological measures, reduced motivation and initiative, and interpersonal conflicts that were affecting their simulated mission performance in ways that the pre-mission psychological screening had not fully predicted. 2 of the 6 crew members became progressively sedentary, spending increasing amounts of time in their sleeping quarters and reducing their engagement with mission activities. 1 developed a chronic sleep disorder that persisted for the remainder of the experiment. Psychologists analyzing the dataset identified a phenomenon they termed the third quarter effect, a predictable psychological deterioration that occurs approximately 3/4 of the way through any long-duration isolated mission. And that has been documented independently in Antarctic winter over research stations, in extended submarine deployments, in long-duration hospital patients, and in other isolated confinement situations. The mechanism appears to be related to the relationship between temporal position in the mission and remaining motivation. The novelty of the experience is worn off. The endpoint is known but still distant. The routines have become grinding. The interpersonal landscape, the same faces in the same spaces day after day, has been fully explored. The mind enters a state of depleted engagement that can manifest as depression, irritability, withdrawal from mission duties, or in extreme cases, reckless or antisocial behavior. On a Mars mission, the third quarter effect would hit during the surface stay phase, when the crew is farthest from Earth, when the communication delay is at its maximum of up to 24 minutes each way, when the workload is highest, when the consequences of errors or interpersonal breakdown are most severe, and when there is absolutely no option for relief, substitution, or early return. A message from Mars takes between 4 and 24 minutes to reach Earth, depending on the orbital positions of the 2 planets. A reply takes the same. A conversation that takes 30 seconds on a phone becomes a minimum 8-minute of exchange of one-way messages, and during periods of maximum orbital separation, it stretches to nearly an hour. You ask a question. You wait. You receive an answer. You respond. The conversation, such as it is, happens in slow motion across interplanetary distances, with no spontaneity, no real-time support, no ability to convey or receive the nuances of tone and expression that make human communication actually work at a therapeutic level. There is no calling a therapist and getting an immediate response. There is no voice from mission control that arrives in time to help with the decision that needs to be made in the next few minutes. There is no family member who can respond to your message before the moment of crisis has passed or resolved itself one way or another. And the factor that distinguishes a Mars mission from every psychological isolation study ever conducted, the factor that makes every analog comparison ultimately insufficient, is the absence of an exit. In Mars 500, the volunteers could walk out. In a submarine, the captain can order the vessel to surface. In an Antarctic research station, an emergency evacuation, difficult and dangerous as it would be, is physically possible. A crew member who develops a mental health crisis that makes them unable or dangerous to continue can in principle be extracted from those situations. Impractical, costly, perhaps never actually done, but physically possible. On Mars, there is no exit. There is no early return. There is no personnel substitution. There is no rescue mission that could realistically arrive in time to matter. The crew member who experiences a psychiatric crisis on day 400 of a 900-day mission faces that crisis in a habitat the size of a small apartment, with 5 other people who are experiencing their own compounding stresses, with limited pharmaceutical options that were chosen and packed before launch, with no medical specialist available anywhere within a meaningful communication timeframe, and with no option to separate themselves from the environment that may be contributing to or exacerbating their condition. The baseline incidence of acute psychotic episodes in the general population is roughly 1 in 100 per year, applied to a crew of 6 over 3 years, with the additional stress factors of isolation, radiation effects on the central nervous system, sleep disruption, physical deterioration, and confinement without exit. The probability across the mission becomes something that cannot be treated as negligible in any honest risk assessment. Artemis II lasted 10 days. The crew was in nearly constant communication with mission control. Earth was visible out the window, a recognizable blue disk that represented home and help and return. Psychological monitoring was extensive. The mission design included careful workload management to prevent fatigue-induced errors. The crew knew that if a genuine emergency occurred, they were days away from help, not months or years. And even with all of those mitigating factors, the psychological dimension of the mission received significant attention in training, in briefings, and in post-mission debriefs. Scale that baseline to 900 days. Remove real-time communication. Remove the visual connection to Earth. Remove the knowledge that help exists within any time frame that matters for an acute emergency. Remove the possibility of early return under any circumstances. What you have left is a psychological environment with no true precedent in human experience, no validated countermeasure for the specific combination of stresses involved, and no safety net if things go wrong in ways that the pre-mission screening and training did not fully anticipate. The mind, like the bones, like the cardiovascular system, like the immune system, like the heat shield, like the radiation biology, is another system that functions adequately for 10 days and becomes something we do not fully understand at 900. And then there is a question that ties all of these threads together into something even larger than any individual technical challenge. If the radiation ceiling is real, and it is, and the heat shield gap is real, and it is, and the physiological deterioration at Mars duration is real, and it is, and the psychological challenge is real, and it is, then why does the narrative that Mars is 10 to 15 years away persist so confidently in public discourse? Why do the timelines keep appearing in headlines and investor presentations and congressional testimony and inspirational videos with essentially the same confidence, regardless of how the underlying data accumulates? Part of the answer is that Mars as a concept does something genuinely valuable. It focuses engineering effort. It attracts investment. It recruits talented people who might otherwise direct their abilities elsewhere. It generates the kind of public enthusiasm that translates into political support for space science more broadly. These are not trivial contributions, but there is also a gap, a real and growing gap, between what the public narrative of Mars colonization promises and what the scientific consensus on its feasibility actually supports. And that gap is not closing. Every year that we learn more about the deep space radiation environment, about the long-duration physiological effects on the human body, about the material science limits of re-entry systems, about the logistical requirements of sustained off-world human presence, the timeline gets pushed further out, not closer in. if you follow the data rather than the aspirations. The narrative says 10 years. The data says we do not know, and possibly not ever, without breakthroughs in several fields that are not on any current development roadmap and cannot be scheduled like a software release. I want to take you back to something Victor Glover said during the Artemis II mission that has stayed with me since I first read the transcript. As Orion cleared to the far side of the moon and Earth reappeared in the windows, he said that the moon is not just a poster in the sky that goes by. It is a real place. He is right, and the more we learn about the real places beyond our own, the more we understand something that the Earthrise photograph began telling us in 1968, and that every mission since has continued to say more clearly. Earth is not ordinary. Earth is not the default state of a rocky planet at this distance from a star. Earth is extraordinary. The magnetosphere, the atmosphere, the biosphere, the water cycle, the living soil, the breathable air, the gravity precisely calibrated for the biological systems that evolved within it, all of it together represents a set of conditions so rare and so precisely suited to us that we have not found anything remotely comparable anywhere else in the universe despite decades of searching. Christina Corwett said something after the mission that I think deserves to be quoted carefully, because it captures something that the technical discussion alone cannot reach. She said that when you have that perspective, when you see Earth from behind the moon, it reminds you how much we all have in common, that everything we need, Earth provides, and that you cannot truly understand that until you have had the perspective of the other. That is not the statement of someone who thinks we should stop exploring. It is the statement of someone who has done the exploring and returned with a particular kind of knowledge. The kind you can only get by going far enough away to actually see what you came from. Artemis II gave 4 human beings that perspective. It gave them something unreachable by any other means, and it returned them with data, both the scientific kind recorded by instruments and the human kind carried in their own perceptions and memories. That is genuinely valuable for everything that comes next. What the mission did not do is resolve the fundamental challenges that stand between where we are and the program's stated long-term destinations. The heat shield performed in an untested configuration, and we will know more about how it actually performed when the inspection data comes in. The radiation environment exceeded baseline models for 7 straight days. The crew built a luggage fort against the cosmos. The re-entry was the fastest crewed atmospheric entry in history. The sun cooperated enough that we did not find out what an August 1972 class event would do to this crew in this vehicle. Those are not footnotes. They are the story. They are what Artemis II actually revealed when you look at the data instead of the celebration. And here is where I want to leave you, because this conversation matters, and I want to finish it honestly. What Artemis II proved is that we can do this. We can send human beings to the neighborhood of the moon and bring them home. That is real. That is earned. That is the product of thousands of people's extraordinary work across years and decades, and it deserves the celebration it is receiving. What Artemis II also proved in the data rather than the press releases is that the gap between doing this and doing what comes next is not a gap we have solved. It is a gap we have more clearly defined, and clearly defining a problem is the necessary first step toward actually solving it, which means that in a real sense, the discomforting data from Artemis II is more valuable for the long-term future of human exploration than the triumphant data, because it tells us precisely where the work needs to go. The radiation problem needs a solution that does not yet exist. Active magnetic shielding for spacecraft. Pharmaceutical protection for DNA against ionizing radiation in real time. Biological research into radiation resistance that could inform countermeasures. These are hard problems at the frontier of physics and biology and materials science, and they require investment and sustained focus, and the willingness to face the fact that we cannot skip past them with schedule pressure and optimistic timelines. The heat shield problem needs solutions validated in the actual environment, not confirmed for the first time during crewed missions. The Mars return re-entry regime needs ground test facilities and theoretical models capable of addressing the physics at 14 kilometers per second. And that work needs to be done before the people who need to trust their lives to those solutions are sitting behind the heat shield. The physiological problems need research programs, real ones with real funding and real duration, studying what happens to human bodies over Mars-class timescales in environments that replicate the full combination of stresses. not just microgravity alone or radiation alone, but both together, for durations approaching what the mission actually demands. The psychological problems need the same kind of investment, with the same kind of honesty about how little we actually know about human psychology under conditions that have never existed before. None of that is defeatism. None of that is an argument against exploration. It is an argument for taking the exploration seriously enough to do the actual work rather than paper over the gaps with aspirational timelines and inspirational language. 4 people went farther from Earth than any human being in history. They saw the far side of the moon with their own eyes, a place that no person had ever observed directly before them. They came home. That is extraordinary, and it is real, and it matters. What comes next will be harder by a margin that the current public conversation has not yet fully reckoned with. And the gap between reckoning honestly with that and reckoning partially with it. The gap between looking at the data and looking at the press release. That gap is where the future of human spaceflight actually lives. Tell me in the comments what surprised you most from everything we just covered. Was it the radiation numbers, the heat shield story, the August 1972 near miss that most people have never heard of, the Luggage Fort? I genuinely want to know what landed hardest for you, and whether this changed how you think about what Artemis II actually meant beyond the celebration. And here is a question I want you to think about and answer honestly below. Do you think we should push forward toward Mars on the current timeline, accepting the risks as they currently stand, the way the Apollo crews accepted risks that were not fully characterized? Or do you think we owe it to the people who would actually go there to solve these problems first, even if that means the mission is decades further away than the headlines suggest? There is no wrong answer to that. It is a genuine ethical question with genuine arguments on both sides, and I want to hear where you land on it. If this kind of deep, honest, data-driven analysis of space science is what you come here for, the subscribe button exists because this is what every video on this channel does. No surface-level summaries, no hype disconnected from what the data actually says, no inspirational framing that leaves out the part where the radiation alarms ran for 7 straight days. Just the full story as carefully and honestly as it can be told. And if this video gave you something today, something that genuinely shifted how you see what humanity is attempting out there in the darkness beyond our magnetic shield, the super thanks button is a direct way to support more of this work. It keeps this channel producing the kind of long-form, deeply researched analysis that takes real time to do properly, and that you genuinely cannot get from a 3-minute news segment. Whatever amount feels right to you means something real to this channel's ability to keep going. The crew of Artemis II is home. The heat shield is being inspected at Kennedy Space Center right now. The radiation data is being analyzed. The physiological data is being collected and studied. The mission is over, but the work it generated is just beginning. And when those results come in, when we find out exactly how the new heat shield configuration actually performed under the actual conditions of the actual mission, the conversation changes again. And this channel will be here when it does. Because the moon is not just a poster in the sky that goes by, and neither is Mars. But they are real places, and real places demand real honesty about what it takes to reach them and survive.